I think that in soft robotics, we are in desperate need. This is like one of the big challenges in this area for more effective, universal, hopefully universal, but at least more flexible, compliant, and more adaptable actuation systems. And it's just so exciting to watch nature and see that in almost every organism that is not a plant, but actually quite a few plants as well, have got soft muscles in them and they're contractile. And yet we don't have that kind of universal thing in robotics except the motor. And that's completely different, right? It's a rotational system. So where is our really effective, scalable, because biological muscle can go from tiny scale to a huge scale, from a really small insect, like the smallest flying wasp, which is so small I don't think you can hardly see it, to a blue whale. They all use basically the same technologies for actuation. Well, we don't have that. And wouldn't it be really cool if we've got that? The motor is like the closest we've got in conventional robots, but we don't have that in ours. But at the same time, I can also say that there is room in this environment, in this research field, for lots of different types of muscles, actuators, sensors, materials, and so on. So I don't think there's like a challenge. We're not doing anything wrong. I'm just praying that over the next 20, 30 years or so, we can produce a universal, scalable actuation system, or call it a muscle if you like, the ideal of an artificial muscle that will be used ubiquitously everywhere.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwiney, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. First of all, congratulations for the new paper. And I think it's very interesting, the actuator design, the concept in microair vehicles. So if you can tell us about what are the challenges of the actuation when it comes to a real application like microair vehicles? What are the challenges? Trying question here.
Okay, Marwa, that's a lot of questions in there. Let me just tease those out a little bit. I suppose the first thing is, what is the work that we at Bristol, in the Bristol Soft Lab, have been developing? And this is work that was conducted by researchers Tim Helps and Chris Romero, who did just an amazing job putting together the designs for this flapping robot system, and with Majid Takavi, who's now at Imperial College in London. And what we've done here is to take some of our technology that we developed a few years ago, called dielectrophoretic liquid zipping actuators. We could talk about those a little bit later, which is the core fundamental actuation technology. And we've applied them to flapping wings. And it seems very simple to say, I'll take an actuation technology in one area and then I'll apply it to another area and make flapping wings. But actually it's quite difficult, because the challenges that we're trying to meet here are to make flapping wings for autonomous vehicles, which are going to be really small. And so therefore you broach this challenge of making micro air vehicles. And air vehicles are difficult enough because of fluid dynamics. And of course, people have been working on this for more than 100 years. But when you go to micro air vehicles, things become perhaps even more interesting and even more challenging. So when you take an actuator technology, what actuator technology is there for moving things, and then you want to put it into a microair vehicle, there are extra constraints for this moving thing, this transducer that turns, in our case, electrical energy into mechanical energy. And they involve questions of scaling. They involve questions of materials. they also still question the underlying physics of the system, and they don't exist without the wing part, which is the fluid dynamics, the aerodynamics. And because we're working with very small wings and very small target microair vehicles, it becomes more complex, and you look at unsteady flows and you're looking at the kind of behavior that insects operate in, kind of the regimes that they operate in. So perhaps we could touch upon that, I guess, in a minute.
Yeah. I think it's also interesting. I think when a paper, the performance that maybe surpassed what already nature had, and I'm curious if you can dig deep into the performance, how you can, advance beyond what we have already, like insects and flapping wings, for example.
Yeah, so we've made some advances here, and of course, lots of groups around the world are making advances in microair vehicles, and our particular niche in this, which gets us into this area, is the actuation. So let me just describe the actuation system, what we consider artificial muscles behind this. And one way to look at this is just to step back a little bit and to look at wings, for example, and say that if I were, as a human, to pretend to have a wing, I'd put my arm out to my side and I'd flap it up and down. And to get my arm to flap up and down, I have to use muscles in my shoulder and in my back and on my chest. And that's what nature does. It uses those muscles in the insects and birds to pull those wings up and down. And so they are linear actuators. If we use that word, actuator, something that pulls, generates a tension. And they are linear because they are muscles. And of course, lots of work in engineering is done looking at rotational systems, motors, and the allied gearboxes behind them. But we felt that doesn't really meet the need for soft robotics. It doesn't really meet the need for these air vehicles. So we've been focusing very much on linear actuation, kind of muscle-like activation. So to do that, we use electrostatics. And there are several classes of electrostatic actuation that people are looking at. One of them, classically, is been used for the last 15, 20 years, are dielectric elastomers, DEAs. And they work on the principle that you have two compliant electrodes and they come together under high voltage and they squash an elastic material. And then when you switch off the potential, then the two electrodes just are pushed apart again because of the stored elastic energy in that material. Okay, so we know that can be used. The trouble is there you've got an elastomer, and that is using some of your energy. There's a limit to how you might apply that in some cases. So what we did was we took the elastomer out of the equation, and we considered, going back to first principles, of just two plate conductors, and then you apply electric field between those two, and then they come together. And we know that when you've got two charged plates and then they come together, the forces between those two plates increases very significantly as you come towards a zero gap. Okay, and that I think has been quoted by Feynman as like one of the strongest forces that you could use. And I think I misquote him, but that's a very good focus. That electrostatics at those kind of very small scales is really important. So the kind of general principle is that if you can harness electrostatics at a small scale, then you can use it. The trouble is we want our artificial muscles, our actuators, the output from our actuators to be at the large scale. So there's a little bit of a mix between those two where we find there's a gap. So what we said is that instead of putting our electrodes parallel to each other, why not bring one end of these electrodes closer together? So you immediately generate a really high force at that point where they're almost touching, but they're not touching, right? Because if they touch, they short circuit. And because you're generating that really high force there, those electrodes will want to come together. Now, in this kind of situation, we don't have anything between them. We just have air, maybe, or vacuum, and there is a force pulling them together. And if they come together at that point but don't quite touch, you put a little insulator between the two. What will happen then is that as you let this structure move, it will start to fold together, and we call it zipping. What it happens is at the closest point, it comes together at a high force, and then that kind of area moves up the structure, and this thing zips together like a zipping clothing. It's a zip, and it closes. So what you can do there is you can take a tiny actuation and you can turn it into a really large actuation because you're pulling things together from a small closing junction into this really big thing that closes. It's kind of neat. Now, that works well, and people have been using this kind of structure in MEMS devices for a while, and they typically operate in vacuum or in air over really small scales. But again, that's that challenge of the physics works very well at a tiny scale, but we want things that are bigger, which is really annoying for the physics. So what we did was we realized that if you could just put a high dielectric material between those two and then let that material be mobile, then you'd actually increase the force. And you can do that. So what we do is at the point where these no longer parallel electrodes, but they're kind of just angled together so that they've got a point where they almost touch. If we put a tiny drop of dielectric material in there, then that increases the forces locally at that point. And then you get this thing zipping together much more strongly. And the great thing about this is that all sorts of fun physics come together. We've got electrostatics, which works really well, especially with a high dielectric material. We've got, so we end up increasing the force at that zipping point, and that extends through the whole actuation movement. But also you've got this extra force called dielectrophoresis, which pulls that liquid into that zipping point and means that it stays at the right place. And it also means that you don't need lots of this liquid. You only need a tiny amount because it actually moves with the zipping point. Okay, so all of this description just says that we can take simple electrostatics and we can turn it from a tiny MEMS-based kind of technology into something that you could use for something bigger. And of course, today we're talking about microair vehicles, but they're still much bigger than MEMS. And ultimately, we want to make artificial muscle structures which are big enough to, put on people's bodies or make large robots from them. So having made this zipping structure, which has got liquid inside it, and we call it, dielectrophoretic liquid zipping, DLZ, what can we do with it? So we've made structures which contract linearly and they expand. We've made metamaterials which are kind of three-dimensional and they kind of contract. You can imagine like a Rubik's Cube that starts off as a cube and then completely compresses down to basically a piece of paper. And then, of course, you switch off the voltage and this thing expands out again. And what we then did was Tim and Chris, and Tim specifically said, well, couldn't we use this for a flapping wing? Because the materials that we're using are two very compliant electrode plates. And if you look closely at one of them and you keep one still and you move the other, it looks a little bit like a flapping wing or part of a flapping wing. So you had this great idea of sandwiching one of these electrodes between two fixed electrodes where you can change the polarity and you can change the charges. And the one electrode in the middle becomes mobile. And so what happens is you kind of have a V structure, which is at the shoulder, if you want, of your insect, where you've defined this muscle, this flapping wing, and then you have a mobile electrode in the middle, which flaps between this kind of V-shaped electrodes. So we got this ability then to take very simple electrostatics, scale it up, put it into a wing structure, and then flap a wing. And there's one great added advantage to this, and that is that there is nothing between the energy generation system, which is the muscles, these kind of zipping structures, and the wing itself. Typically, if you're making a microair vehicle, you're using an actuator, maybe a piezo actuator, something like that. It's got a very small stroke, so you need some gearing system to turn that into enough flapping, a flapping strain, flapping movement for the wing to flap. So here what we've got is a system that not only scales electrostatics up into a relatively large, in this case, centimeter scale, but of course we can make them smaller, flapping system, but it also gets rid of any gearing between the two, which makes the system more efficient. So I think what we're doing here is again, we're playing on the physics working for us and also the structure working for us, because we don't have the gears. And hooray, I really like it when we can say we don't have motors because they've gone out the window. We've got this kind of linear actuator or this electrostatic actuator, and we've got rid of the gearbox. Hooray, it's just direct connection. That's what insects use, right? They have a relatively direct connection between the muscles in their body and their flapping wings. So I suppose all of that basically describes how we took a relatively simple, when you look at it, technology and turn it into a flapping wing.
Mm-hmm. That's excellent. Maybe I want to ask you here about the material part and actuation and the architecture or the shape or the material. Which one is significant when it comes to scaling or coming up with interesting design, the material part or architecture? Which is interesting to you or significant?
Well, but that's the thing with soft robotics and these kind of structures, you can't have just materials on its own without the design. You can't have the design without the materials. We're working out the scales where material stiffness and geometry are so carefully balanced. It's not like we have a steel girder and it doesn't matter whether it's really big or really small. It's still got basically infinite stiffness in practical applications. Actually, we're dealing with these compliant materials, so we need them to bend, and we need them to bend in a certain way dynamically. So that is a delicate balance between the geometry and the materials. And an example of that really is in the shape of the electrodes against which that central flapping electrode presses or is attracted. So you can imagine that you have a thin ruler, and then you're going to twang the ruler. We do this at school, right? We hold a ruler in our hand, and we put it on the desk, and we go twang, and it goes boing, backwards and forwards, right? So you've just got a vibrating beam, and that vibrating beam and the movement that it generates will depend on its stiffness. Of course it does. And that's kind of what a flapping wing is, right? It's a resonating, hopefully at resonance because it makes it more efficient. It's a resonating flapping structure. In our case, because the root is fixed, it is actually like a flapping ruler. So we've got this energized flapping ruler flapping backwards and forwards. And as it bends in a characteristic shape. But if you put a heavier wing onto this electrode, or if you make the electrode out of something softer, like a thinner piece of material, then it bends more. It bends in a different way, in a tighter curvature. If it bends in a tighter curvature, it means then you have to make your counter electrodes, the bits that are pulling and pushing, a different shape. So your question is really interesting. What is the most important part here? Is it materials or is it structure? It's both. You kind of need to challenge those two. And what we're doing now at the moment with our research is to try to make this system smaller, an order of magnitude smaller. And to do that, we do have to look at the materials and the structure again, probably change the shape and also change the materials.
Yeah, maybe I want to ask you your views on actuation when it comes to soft robotics field. This is technique you mentioned, I think, very interesting. I find it very interesting. But when you have the scope of the actuation, is there something you disagree with? And you think we have to focus more in this direction of actuation, this class of actuation? And maybe you disagree with this vision.
That's a really good question. What do I think there is something wrong with the way we approach actuation, or is there some challenges that I feel we should address in actuation? I think I'm going to answer that question. I feel like that's kind of where I think that's kind of where we're going. I'm not sure. So I think that in soft robotics we are in desperate need. This is like one of the big challenges in this area for more effective, hopefully universal, but at least more flexible, compliant, and more adaptable actuation systems. And it's just so exciting to watch nature and see that in almost every organism that is not a plant, but actually quite a few plants as well, have got soft muscles in them and they're contractile. And yet we don't have that kind of universal thing in robotics except the motor. And that's completely different, right? It's a rotational system. So where is our really effective, scalable, because biological muscle can go from tiny scale to a huge scale, from a really small insect, like the smallest flying wasp, which is so small I don't think you can hardly see it, to a blue whale. They all use basically the same technologies for actuation. Well, we don't have that. And wouldn't it be really cool if we've got that? The motor is like the closest we've got in conventional robots, but we don't have that in ours. But at the same time, I can also say that there is room in this environment, in this research field, for lots of different types of muscles, actuators, sensors, materials, and so on. So I don't think there's like a challenge. We're not doing anything wrong. I'm just praying that over the next 20, 30 years or so, we can produce a universal, scalable actuation system, or call it a muscle if you like, that ideal of an artificial muscle that will be used ubiquitously everywhere. We see it a lot in science fiction. They will say, here's my science fiction robot, and it's animated or it's CGI, and behind that, there's some really cool actuation technology, whatever it is, don't know what it is, but it's working there and it's working in another thing in that same film or so on, and they've got it, but we don't quite have it yet.
Mm-hmm. Maybe I want to ask you, there's something was counterintuitive or be surprising in this paper, or maybe if you have something you would like to mention, was counterintuitive to your intuition when it comes to the performance or the design. Do you have this scenario happen maybe in the paper, or maybe you can recall from any past experiences here?
Yeah, so there are some interesting things about this particular structure, which are kind of counterintuitive. We found that there is a kind of delicate interplay, if going into the detail, delicate interplay between the electric fields in the various pieces of material that we use to construct this thing. And you'd hope that you'd have a really simple rule that says that, for example, if you have got an electric field and then you've got a dielectric material between the two, you can store more energy in that field, in that structure, effectively a capacitor, if you have a higher dielectric. And that's exactly what capacitor law says. Absolutely fine. And then you would think that, with that being the case, you'd get more actuation out of such a system. But you've got this interesting interplay with electrostatics quite often, in that you do want to increase energy storage, but you are increasing typically the electric field, which means you're more likely to have breakdown. So there's this real delicate interplay with these structures, and it works in ours as well, where it was kind of counterintuitive to me to look at this and think, oh yeah, we want to have the most dielectric constant of our material to get the highest energy density in there. And yet Tim would turn around to me and say, yeah, that's great, but you know what? You can't do that because it'll break down. So you need to have something here which has got a higher breakdown strength. And that may have a lower dielectric constant, therefore it stores lower energy and actually results in less energy coming out. But it means you can realize it. So this kind of notion that physics says this is ideal and we can get this power out of our muscles, and yet we can't quite go there because another bit of physics says that that's not going to work because it's going to break. So you have to rely upon the other bit of physics as your limitation. And that's a little bit of a surprise to me sometimes. What can you do? Your physics is physics. You just have to deal with it. But the trade-off between those two is really interesting. But it's still we've still, with those constraints, been able to make these artificial muscles, which have the energy density, power density of mammalian and insect muscle, which is pretty good, right? If you can make energy and power density of your actuator as good as insect muscle, then you should be able to make something which is as good as an insect. That's like the ultimate goal, right? In terms of flying or capability or size or whatever.
Mm-hmm. Maybe I want to ask you in the way of the design and thinking, because in the paper, for example, we mentioned how we can surpass the performance, what we already have an insect. And I want to ask you, when it comes to design a space, what is the first thing you look for that we already look for by inspiration, but it seems that you can surpass this stage and coming up with something beyond what we know. What is the first thing in the design space you look for to achieve the goal here?
You're absolutely right there, because the design space quite often for us engineers is quite small. And we would say we're working in this area of a particular type of a flapping actuator or an actuator that drives a flapping wing, and we will then evaluate it and we will produce a metric that says that this muscle in this configuration is as good as insect muscle. And it works in that small design space. But if you were to go and look at this bigger space of all actuation in robotics, you wouldn't be able to achieve that, right? That's kind of typical thing of whereby you can say that your actuator can produce really, really big strains. Like, so you can move out a meter. Or you could say that my actuator could lift 1,000 times its own mass. But typically, and we have the same challenge as well, you can't do the two at the same time. You can't use the same actuator for lifting something 1,000 times its own weight, 1 meter. It just can't do it. And yet that's the kind of thing that nature in its muscles can do. I'm just giving you as an example.
Mm-hmm. Maybe I want to, thanks to close the end, I have a question here, but I want to go for the failure and redundancy in Ziming actuation. Can you tell us more about the design here for redundancy and would it fail exactly?
Well, if you take the actuators that Tim and Chris have developed here, these kind of flapping wing actuators, they have got failure. They're pretty good. We've found that we've got to millions of cycles, which is good. If you think of an insect, it's going to flap its wings for many, many tens of millions of cycles during its lifetime, depending, right? Some insects don't live very long, right? Some of them only live 24 hours or so, which is a real shame. But many flies or insects are flapping their wings for many, many more cycles than that. At least I think they are. I have to go and check on that. But the failure modes for ours are there's electrostatics, and as I said before about the material fatigues electrically as well as mechanically, which is very interesting, and so you get breakdown of the materials. Of course, you've got a flapping wing, so your materials should be elastic and efficient and resilient. I think that's a really important word, where you get as much energy out of the system as you put in, because any wasted energy it's got to go into somewhere. And it goes into heat, or it goes into, causing some kind of damage in the material. So the flapping electrodes that we're using here are steel strips. They are spring steel. And spring steel has got a very good resilience, right? You can hit it and it oscillates a lot. It's got a lot of return energy. It's got very little losses, hence we use them for springs. But they may still break. Typically ours don't break. What is a challenge, though, for flapping wing insects or flapping insects? No, sorry, I shouldn't say that insects. I keep thinking of that. The flapping wing robots that we're looking at here, which are a little bit bigger than insects, is that the wings are very difficult to design. So insects and others, organisms that are running at this very small scale with this unsteady flow, they have to use quite dynamic wing pitching actions, right? You may have seen the videos which show that insects can have very extreme wing pitches, and they can move their wings in figure of eight shapes and so on, all that to control the flow at very, very small scales. And yet those wings that they've got are pretty passive in themselves, and a lot of the work is being done at the shoulder, or being done in the body, as it were. But ours wings aren't like that, so we have to generate that pitching movement. The wing has got to shift forwards and it's got to shift backwards as it pitches. We have to do that mechanically. That involves things like rotational joints and so on at a very small scale, and they can break, right? And it's very difficult to make something small and complex that flaps backwards and forwards at 100 times a second that doesn't break. And that's still a challenge for us. Others have looked at this and they have their own solutions, and of course we're looking at ours too.
Mm-hmm. Maybe a few questions left. I want to ask you what other question with this paper you still try to maybe answer here in the next maybe few steps for in the field. I don't know what other question do you think you still want to answer here?
Oh, for this work, I'm really excited about this work, right? So the work we produced here shows artificial muscle-driven, electrostatic actuator-driven flapping wings. The wings are only part of the problem, right? You've got to be able to do something with it. And our wings exist on their own, but they don't have the body, and they don't have the head, and they don't have the power system on board, and they don't have the computation, and they don't have the control system. So it's one part of the puzzle we've got here. And so the next thing is to look at what are those other parts of the puzzles. And if I can list them on my fingers, there's power, and power requires a power source. Unless you're going to have your insect or MAV tethered, which is not really a good idea for an MAV. You want it to be autonomous. So it's got to have onboard power, which is a challenge because you've got to have it lightweight. So what's the energy source you use? And you could use lithium polymer batteries and so on. So there's questions behind that. There's questions on the control and the electronics, because we're talking about electrostatics, so high voltages. You need high voltage amplifiers. You need a way to turn battery level voltages of 2 or 3 or 4 or 5 volts up to 2 or 3 or 4,000 volts. And it's a challenge, but we can do it. And then there's the control system. And we know that control of unsteady flow in microair vehicles is an interesting challenge. So that's a nice one to look at. And packaging all this up into something that is resilient and can move around in free space that's really exciting. And then the final challenge is take all that at maybe centimeter scale and make it millimeter scale. That's a really exciting challenge. So we'll put all those together, and I think we've probably got another 20 years of work budget, maybe 10.
Yeah, maybe I want to ask you what makes you fulfilled and satisfied. I think maybe in research, in general, what makes you fulfilled and satisfied?
What makes me fulfilled and satisfied? Well, actually, showing this kind of work to people in the community and more broadly, and for them to look at it and say, yeah, that is really interesting. And to show the work that Tim and Majid and Chris have done in this area, right? They've put all the work into it. I just stand back and I look and I say, that's just excellent, right? And to show them that they have really produced something novel here. And then the next step is, of course, to take this forward. And what's going to happen next? Us as engineers, we look not just at what we're doing now, but what we're doing next. I think that's what sends us to sleep with a smile. Well, I hope it sends us to sleep with a smile on our faces.
Wonderful. I don't know if you have any final words like to say from the software robotics community, people listening. Any final words like that?
I think flapping air vehicles and microair vehicles is a really exciting area to work in. And we've started this over the last few years. I think that there are some amazing research groups working on this in the world. And I hope more people are going to work on this because it is a really exciting area that we haven't really got a hold of just yet. There are so many insects in the world. There are so many flying things in the world, billions and billions of them. And how many robot flying things are there in the world? Is probably only a handful. So there's a long way to go.
Maybe a quick question. If there's any example in nature very interesting to maybe still want one day to replicate example.
I think the bumblebee is the most exciting because there used to be an idea that that bumblebee, which is a big fat bee. For those who don't know, it's a big fat bee with quite short wings, and it looks like it shouldn't fly. And then lots of people thought about this, a couple of decades ago, and said, "Oh no, the physics says it shouldn't fly." And I thought that was such a good thing that the scientists looked at this insect and said, "Oh, it shouldn't fly." But I think that's really exciting because it's dynamic, it's capable, it lives very successfully, and it contributes to the environment by pollinating plants and so on. And yet it's such an exciting, interesting